Welcome, everybody, and thank you for joining this webinar hosted by Robust Intelligence. Today, we're going to be talking about a recent paper, Real Attackers Don't Compute Gradients, Bridging the Gap Between Adversarial Machine Learning Research and Practice. And this is a paper that was presented just last week at the first IEEE conference on secure and trusted machine learning. And I'm honored to host today my co-authors, who I'll be asking to give more context and to give a deeper dive into this work. More time than was, kind of possible during the conference itself. So today we have with us Dr. Giovanni Apruzzese, an assistant professor in data and application security at the University of Liechtenstein. Dr. Fabio Pierazzi, assistant professor in cybersecurity in the Department of Informatics at King's College London. And Dr. David Freeman, research scientist who works on external data misuse at Meta, the parent company of Facebook and Instagram. And I am Hyrum Anderson. I'll be hosting today at Robust Intelligence. You can find more about biographies, backgrounds of each of us on the webinar registration page. Before we get started, I do want to recognize that we're actually missing two co-authors from this panel who are unable to make it. We have Dr. Kevin Roundy and Sigino Dambra, research scientists in the Norton Research Group, who made really significant contributions to the paper, but unable to join us today. Those who want to follow along, we're going to drop a link to the archive paper in chat. And maybe we might be referring to this from time to time. And also during our discussion today, please feel free to submit any questions that you have for the authors throughout the webinar into the Q&A channel in Zoom, and we'll do our best to address those. So with that, let us begin. I first want to ask our co-authors here to provide a little bit of context about how this paper came to be, why this message is important. Fabio, I want to start with you because my first invitation to participate in this collaborative research was in an email that came from you. So how did this come about? Give us the backstory.
Yes. So the backstory was that me and Giovanni were, even before DACSTOOL, we were collaborating on a research paper, and after DACSTOOL came to an end, we scheduled another meeting to have an update on actually that project. But we ended up discussing and brainstorming on some aftermaths, in a sense, of discussions that we've had during the DACSTOOL seminar on security of machine learning. And we were particularly, everything I think started also from the concept that is in the paper about ML models versus ML systems, to the fact that most academic research was focusing only on protecting individual machine learning model, whereas real world system should be more complicated, right? And also, so we were reasoning also about how should we even change the threat model of our paper, and we started discussing, and then came to the idea that, but maybe there's more to say, right? It's not just about this other paper having a specific threat model. There's more of a message to give to the community that can come out of the DACSTOOL seminar. And so I decided to drop an email to all you guys, basically all the co-authors. And the idea, since there was this first edition of the IEEE Safe and Trustworthy Machine Learning Conference, SaTML, if I remember the acronym correctly, they had the position paper track. So we thought, yeah, why not? Like, we could send it's just 5 pages, so we should have enough time. And I think there should be an important message to deliver to the community about this, and to which both academics and practitioners can contribute to.
Fabio, you mentioned almost in passing Dagstuhl. I think there's probably most of our listeners today aren't familiar with the Dagstuhl conference. Giovanni, would you mind giving us like what is Dagstuhl, why, what was the thing about, and kind of what were the themes that contributed this paper?
Mm-hmm. Yeah, certainly. So Dagstuhl, it was a magical experience for me. I think I said this when I presented myself at the seminar, that I never heard about it like before I started my PhD. I heard it like very briefly. I read it in some papers, but I didn't truly know what it actually was. And even during this SaTML conference that I attended last week, a lot of people asked me about it because apparently it's not widely known outside perhaps of Europe. And well, in our case, it was like an event in which around, I think, 40 people attended, and they came from both academia and the industry in our case. And it was about the security of machine learning, and it was like a week-long seminar in which people from this community, security and machine learning, they met together and they reasoned, they talked, they enjoyed some time together. I think that in our case, we also had advantage of that being one of the first events that were held in person after the pandemic. So I think that a lot of people truly wanted to say a lot of things to others. So I think this promoted the conversation that were held there. And but it was a wonderful experience to me because it truly allowed me to, and I think also other people, that all the other attendees of the seminar, to really speak their mind and trying to get the opinions of others. And I think that a crucial point in the seminar was at the very beginning. I don't know if you remember, but I was thinking about it recently, that there was Professor Pavel Laskov, who was among the organizers, who asked a question addressed to all the people there and asked who here has a machine learning background and who has a cybersecurity background. And I remember that throughout the seminar, when I was talking with people who had, I raised my hand for the cybersecurity group, by the way, but I remember that whenever I was interacting with people who raised their hand for the machine learning background, I tended to receive very different opinions. And I think it was kind of the starting point also of this paper, because one of the reasons why we decided to submit this paper to this conference was to try to bridge a gap between these two communities, like cybersecurity, like the practical cybersecurity one, and the research-focused machine learning one. And I think that, like, given the good reception of the paper, we kind of got our point across. But this will be, we will have to see about that in the future.
So to me, it stands out both the beginning of the Dagstuhl seminar when we kind of set that up, and the ends when kind of we were wrapping up, and some of the folks, including David, gave some statements about what real attackers are like. Like, for example, what you might experience in a system that's put out by Meta. David, you've been involved in academic conferences about adversarial machine learning for quite some time, and also you've been on the practical side of fighting abuse at Meta. Can you kind of summarize generally what some of the main differences are that you see that exist between the kind of commercial practical applications and the academic research that you've been trying to communicate over the years?
Yeah, thank you. I was, you prepped me for this question. Now my list has gotten extremely long. So I'll try to keep it short. I think one of the biggest ones is scale, especially at where I work. We work on Facebook, Instagram, WhatsApp, a few of the other products from Meta. And we have billions of users, making trillions of requests a day. And any of we don't know which ones are malicious, which ones are trying to scam people or phish or steal data or whatever. And just having this amount of data and having to scale up anything we build to address such large systems is a big difference. in academia, I mean, data is sort of gold, right? Like it's very hard to get data for legitimate reasons because of privacy, user sensitivity, business sensitivity, these sorts of things. So the pattern I've observed is that like in academic research tends to focus on more and more complex analyses of sort of the same data or similar types of data. And what we have to deal with is really kind of the flip. I mean, we often go with the simplest thing, often linear models or random forests on more and more complex data. And so understanding, being able to bridge kind of the algorithmic complexity and the data complexity is one big difference. I guess the other big difference is that we don't know the answers in industry. Again, if you're the best research papers address this, but I do see a lot of papers where it's like, okay, we have our labeled data set and here we're gonna run some classification. In industry, getting the labels is the hardest part. Like, because if we knew how to label everything, we would just do it and block everything bad and it'd be gone. So even what do you even tell a human to look at for some of these problems to produce labels? How do you scale that up to something that could train a classifier? And just like how do you deal with noisy labels, right? Labels that they're probably pretty okay, but maybe only 90% are correct. How does that affect modeling and that sort of thing? I think I'll pause there.
There's more, and I think we'll touch on many of these themes as we dive into the specifics of the paper, David. So feel free to chime in some more. Related to the context now, we're now, for the listeners, we're kind of diving into some of the meat of the paper that includes a survey of 100-some academic papers that Giovanni primarily led over the last several years. I was wondering, Giovanni, if you could kind of summarize some of the findings as you reviewed these papers. This was not a finger pointing exercise, as we note in the paper, but a review of kind of the state of thinking in academia. I'm wondering if you could sort of point out some of the trends as it relates to adversarial machine learning in academia, as opposed to what kind of David has brought up about the practical considerations.
Yeah, so first of all, I was not alone. And most of them, I reviewed them by myself, but I got a huge help from Savino D'Ambra, one of the other authors. He allowed me to do some self-check about try to reason if my findings were correct, because it was pretty hard. This was something that I found out. Some of the things that I analyzed when I was reading through the papers was pretty straightforward, like figuring out if some paper used deep learning or shallow learning, or like what we call as shallow learning, like linear models or random forests, for example. That was pretty easy. I could do that by myself, but there were some. One of the things that we tried to look into was what kind of threat models were considered in the papers, what kind of capabilities, knowledge, goals the attacker had. And these things were pretty hard to figure out. There was one of the things that we highlighted in the paper is that there is some inconsistency in the way terminology is used in this domain. And especially if you try to compare papers, like it's not truly possible to compare these papers. Sometimes one paper says, we assume a white box threat model, and they say that the attacker knows everything about the training data. And another paper that maybe is also assuming a white box attacker, they say the attacker does not know anything about the training data. And they both claim to be a white box attacker, but this part, the training data, sometimes is known, sometimes is not known. And this was one of the biggest inconsistencies that we found. And but something I want to stress is that taken individually, every paper is correct. I mean, if you look deep enough, you will find that the envisioned scenario is correct. The problem is when you try to abstract everything and try to see it from a high level, you see that there are some things that are not truly compatible and makes it hard to try to draw some common grounds on the papers. And about trends, well, something we noticed is that there is a huge imbalance when it comes to what kind of machine learning models are considered. There is for example, most papers that we looked into, they only focused on deep neural networks, and most of them they focus on images. I say that around 60% of the papers we looked at, they were focused on image data. And basically what they said is, yeah, we create a model trained on MNIST or ImageNet or SciFar, and we perform the attack there, and these are our findings. And then from there, the idea would be to generalize every other type of machine learning model in the world. But the thing is that reality is far more complex than that. And in fact, during the conference, I did receive also many questions about, what to do if I have tabular data, or if I use other machine learning models. And the idea is, yeah, probably one of the things we should do is try to explore also other types of applications of machine learning. Other things we noticed was that there is, in most papers, they tend to overlook the cost or the economical factor of an attack, which is something that real attackers do take into account, not just attackers also, but defenders as well. This is something that we do try to emphasize in our paper, because this is perhaps one of the reasons why research and practice are currently going in two opposite directions. And other relevant things, that there currently is like a kind of simplistic assumption that most papers, they only consider models and not systems. Because in reality, machine learning models are just a component of a much larger, much more complex machine learning system. And if you do not consider all the relationships that exist between the machine learning model and the other components, then you may end up with an attack that, perhaps it may work against the model, but it's uncertain whether it will truly work against the system, and hence, would an attacker truly use that? This is something that we try to reason. But I think this was most of the most important findings that we found out by reading recent literature.
I think this alone was just like a super interesting finding that, for example, out of the papers reviewed, almost 3/4 were about attacks, not defenses. Most of them were about evasion attacks, even though industry surveys suggest that the greatest fear is in poisoning. So there's like some interesting dichotomies about what kind of might represent low-hanging research directions and what actually is keeping David Freeman and other colleagues in the industry up at night, right? So we have one question, Giovanni, maybe is good for you to answer with regard to terminology inconsistencies, white box, etc. Do you think that that's caused by machine learning researchers not understanding kind of basic, not understanding the terms in a way that a security practitioner or is there misunderstanding about the terms, or is it something more fundamental?
Well, I think that it may be one of the reasons. I'm not a practitioner, so I don't think I'm the best person qualified to answer this question, but I don't think that in practice, people who develop defenses, they say, oh, we need to propose a defense against a white box attack. I don't think they reason in that way. But there are, I think one of the things we mentioned in the paper is that even the term adversarial sometimes is kind of overused. And another thing is access. This is another term that it's used in inconsistent ways among papers. So I think that perhaps, literature focuses on literature. So papers, they try to frame things in a way that is similar to previous papers. And so they use the same terminology, but sometimes if you look deep enough, you see that there are differences that are kind of significant. So perhaps this is one of the reasons. But I see David wants to mention something, so perhaps he could share his perspective.
Yeah, I was just gonna say, I mean, I think sort of within the communities, there's different proposals, and this is, and but what things should mean. And this is kind of a healthy, normal part of academic discourse. I think between the communities, it really is like of academia and industry, or ML, academia, security, and so on. Like, I think it really illustrates a lack of communication, or gaps in communication, of really not understanding the other's problem and what they're really worried about, and trying to get to.
And this is one of the points we make in the paper, right? That the need for more, like, fewer boundaries in that collaboration. Fabio? Fabio, I think
yeah, sorry, I was muted and I clicked something wrong. What I wanted to say is that I think it's not only a problem in adversarial machine learning literature in general, it's something that happens between communities, like using different languages. It's something sometimes natural that happens. It happened also with cloud computing. Now, what is consolidated to be cloud computing had many other terms before. But staying more on the machine learning side, I guess also when we cybersecurity researchers started to try to use machine learning for solving security tasks such as malware detection, I think we also started to misuse machine learning terms a bit at the beginning. One that is inherited that struck me when I was talking with pure machine learning people is the way in which we tend to use sample. At least in many papers, we use sample as any malware, but for a statistician, the sample is a sample from a distribution, and there's a very specific meaning, right? So I think in this case, communication is key about not only practitioners, but also different academic community, like computer science communities or any real community.
I want to get each of your thoughts on one particular element. The title of the paper is "Real Attackers Don't Compute Gradients," and I think what that refers to is that in sort of academic adversarial machine learning research, we conduct evasion attacks where we have, we'll say, white box access to a model. We compute a gradient, we take a step in that direction, and we do this in an algorithmic way to confuse the model. But, all the evidence about what's actually happening by real attackers in the wild has nothing to do with a mathematical construct of a gradient, right? So I want to, maybe David, I first want to turn to you. There was a notion at the end of Dogstool that I think three of us, you and me and Kevin, each pointed on. That's like real attackers actually just guess. And I want to peel the onion. Like, why? What can you say about what real attackers do? Why are they successful in doing the simpler thing?
Mm-hmm. Yeah, they guess. But usually these are educated guesses based on their experience, their understanding of the system or products being attacked, and their goals, right? I mean, real attackers are just like the rest of us, want to get the maximum gain for the minimum effort. And these systems are incredibly complex, and which just means there's a lot of ways for them to be leaky or have vulnerabilities. So there's an example in the paper around posting spam on Facebook. And to post spam, you come up with your content, you post it, and then you want to kind of distribute it widely. And there's any number of ways to use the product as designed to do this, right? The product is designed to post and share content. And so the part about detecting the content is just one element, as we talk about. Is this image an ad for something, that's banned, right? For example. And so, I think there's definitely the other example in the paper about image manipulation is showing that there's a lot of simple things you can do to fool image classifiers that are not gradient based. And so then it just comes back to what can they do for the minimum cost.
I love it. I think we have several examples in the paper. The Facebook, the Norton researchers had this excellent analysis of real attackers against phishing detector of websites and how they evade that. That is actually quite clever but unsophisticated, right? And then there's evidence of the paper. Colleagues and I have run for the last 3 or 4. Maybe it's 5 now years, this machine learning evasion competition where we are recording how real cybersecurity researchers try to evade machine learning models, incentivized to do so. On this last point, I'm wondering, Fabio, if I could turn to you to kind of, summarize maybe some of the learnings from that we've gleaned from this security evasion competition. What is it like? What have we seen about this? What's important to real attackers?
Yeah, so sure. I mean, I think that, by the way, thanks for running these competitions. I think they're, both very funny and can be very learning opportunities also upon reflection afterwards on what's the outcome. Like in this case, we decided to study specifically one of the competitions in which there were like 10, so the contestants were given 10 phishing web pages, and there were like 7 phishing detectors that they had to evade while keeping the look and feel of the pages. So maybe don't fully quote on me on the details, but the general principle is that they had to create this evasion and they could query the detectors to get the probability of being malicious. And of course, the objective was to evade all 7 detectors while having the minimum number of queries submitted, right, as requests, which, by the way, also in in a sense, in black box attacks research, it's one of the common cost metrics used by academia, right? You want the attack is more powerful if it requires less queries, and it turns out that, of course, I mean, the winner of the competition here was the team that had the least number of queries. But upon inspection, when they had to do a write-up of the challenge and how they solved it, one element I forgot to mention is that there was also a public leaderboard with the other queries of the other teams and some information. So the winning team actually, in a sense, possibly spent the most time and was waiting also to see the results from the other team and how the other teams were doing as a sort of side channel to then decide their own strategy, right? And of course, in this case, they were trying to minimize the number of queries because it was part of the challenge, right? And what we can learn from this is that, well, of course, it was a simulated scenario, so with all the limitations of the case, right? It's not necessarily the real world that you have this group of contestants actually attacking a system together. But at the same time, it kind of shows that maybe number of queries is not the right cost metric. It's kind of maybe there are other things to take into account, and we reflected a lot also about on the domain knowledge that you may have or additional information about the system you're targeting, and how much time it takes for you to both maybe develop even the software for the solution and gather the information. And funny enough, sometimes I remember that even the idea for the paper came up because at the previous competition, there was even the winning team that didn't even use traditional adversarial machine learning to evade the target system. So they, in a sense, they use like the simpler methods that David was talking about, which I found I found it very interesting. So I think, but this is one of the lessons from this analysis of this competition.
Thank you, Fabio. What I want to do now is kind of take a deep dive into the content of the paper. In the paper, there's, I don't know, a dozen different observations and positions in this position paper. And maybe it would be worthwhile for us to kind of review them. And if you want to jump in and make a comment, a clarifying comment, we can do so. But I think if you look at the main, the meat of the paper are centered around some statements, some positions, some observations that are colored in a special way in the paper that you can see. One of them we've already brought up. It's about the distinction between machine learning models and machine learning systems. I want to just dig deeper. So this is a thing. Giovanni, David, like why is this distinction important for practitioners? And like, how true is it? How true is it that all machine learning products are actually systems, not models?
So I guess speaking as someone who implements implements these things or works on a team that does this. I mean, everything is a system because, right, the users don't have direct API access to a model where they, input some features and get a score as output, right? Everything is wrapped up. And the models are there. Models are there to make decisions, to make business decisions. In a spam example, should this content be allowed on Facebook? And all that matters to the user, to both the attacker and the ordinary user, is the ultimate decision of the system. So if the attacker can get the model to crash and not give an output, then they win, right? Then they didn't have to compute any gradients or anything. So this is really the key. The key point is like everything. Everything is there for a reason, and the attackers care about the reason and not the underlying implementation.
I think it's interesting to point out, like if you look at attacks in the wild, so Microsoft Tay or the recent ID.me face recognition, in very few cases did the attacker even realize that they were attacking a machine learning system, right? Like machine learning was not even part of the calculus of the attack. It was just happened to be something that they were trying to evade. The one maybe specific exception to that is the excellent work that Kevin and Savino Dambra brought at Norton about the phishing detector, where they were actually tricking out the images specifically to evade features in the machine learning. But most others, like the attacker doesn't even know that it's machine learning system under the hood. It's a unimportant detail, right?
Yeah, and if I want to say something about this, is that something we mentioned in the paper is that there are some kinds of system which we called as invisible, because if you consider the specific case of the phishing website detector, it's also an attacker that creates a phishing web page. The attacker does not know that their supposed victim is going to click on it, and whether the page is actually clicked and detected or not by the detector. I mean, because in the case of the phishing web pages captured by the company that Savino and Kevin analyzed, the page was analyzed by a system which was analyzing just the traffic of their clients, which were not. I mean, the attacker would not be able to access the decision of this system. So sometimes the output of the system is not even available to the attacker at all. And this is an additional barrier that is rarely found in research papers. Like sometimes you see, okay, the attacker does this, and then they receive this feedback by the model or the system, whatever. But sometimes this feedback may not be even available to the attacker at all. Or if it arrives, it will be after a long time. Maybe after 1 week, they will say, oh, the page that we created, nobody clicked on it. But it will take a lot of time before they are able to realize this. It's not like, the page was analyzed by the system, it was blocked, and now it's we can refine our tactic and because we reverse engineer the system in this way. So this is something that it's a complexity of a system which you do not see if you only consider the model itself.
But would you agree, though, that from a defensive perspective, if you're being proactive about attacks, yes, like attack the model in isolation. That's the taking the white box threat model could be a good thing because it's a worst case scenario more than what the attacker might be dealing with. Would you agree with that statement, Giovanni?
Yeah, I say that if we were able to make defenses that always work in white box scenarios, that would be wonderful, right? Because we would have all models to be protected and we would not risk anything. But systems, they can fail in a lot of other components, in a lot of other parts. So from a practical perspective, again, this is just my idea as a researcher, from a practical perspective, there may be also value in investigating defenses that may not work very well in white box scenarios, but may work well in like gray box ones, or like in cases where the attacker has some intermediate knowledge, because this is probably what happens in reality. David?
Yeah, I think that's a good point. So I wanted to follow up. I think when you were talking about, the attacker doesn't see, the model score was 0.9 and therefore we blocked it. The attacker just sees, well, no one ended up clicking on this phishing page, and so that's. I don't want to say we should be relying on like security by obscurity. But certainly reducing the amount of information given to the attacker is helpful. Making normal and attack responses look the same. Like you'll typically say, most sites that have a login, when you get something wrong, it'll say wrong username or password rather than giving that information of which one is wrong. Which is of course a trade-off between security and usability. The other point I was saying around attacking for defenders, attacking the model specifically to prove robustness. Like, yes, this will make the system more robust, but I guess what is the cost, right? What is the opportunity cost? Where could we have been investing our defensive energy? If we weren't looking at white box attacks and I guess we have a different term for that in the paper. Full information attacks. Trying to move away from the black and white terminology. And anyway, so is simulating and building a defense against this kind of attack the best use of our engineering resources when there's all these other parts of the system that could be exploited? In my experience, typically not, but could be.
So, David, you brought this thing up that I think is brilliant. It's this common refrain in security that we say there is no security by obscurity. And maybe the pushback in machine learning is, there might not be complete security by obscurity, but it doesn't hurt, right? It doesn't hurt to obscure a little bit and maybe raise the cost, elevate the cost to an attacker, right?
Right. Well, the cost of obtaining information, really, because that's what the attacker really cares about is bits of information.
Fabio?
Yeah, I was about to add also the same comment in a sense that I guess it's about raising the cost. Because, of course, security by obscurity would not solve the problem. But I guess that from a practical perspective for companies, it would make sense. At the same time, I also think that so security is an imbalanced game, right? It's like as a defender, maybe you have to protect a building, but an attacker just needs to break any window and maybe they can get in the building, right? So it's the defender's job is much harder, and it's about creating these incentives on the attackers. And about the robustness of models, I think what is also important, I mean, making the models perfectly robust, especially in some cases, could even be impossible, like maybe in the case of images, like perfectly robust to any type of attack. But one thing that is also important, I feel, is we should try to maybe also quantify this concept of cost better and try to understand, given a certain model, what are the real, like, what is the risk, right? It's that we are subjecting to, because even if in a sense we're computer scientists, I guess that in companies, inevitably, there's like a lot of software engineering and engineering involved where you have like real world limitations to consider, I guess, and you have to prioritize things that you want to protect against, and or you may be willing to take a risk if, of course, there may be no perfect absolute defense, but maybe depending on the specific deployment or application, you may evaluate that a certain risk is acceptable. I guess it's more for us to have a better understanding as well.
So we brought it up now a couple of times. Just want to point out there's a specific point in the paper is that economics is the primary driver for practical cybersecurity, both for the attackers and for defenders, and how to prioritize defense. So can we peel the onion there? What are, like, how does one measure costs? How does one measure costs practically? How should we do it academically?
I think this is an interesting point that we raise, because and I think this is also one of the reasons why we see little or like few papers that try to go beyond the queries, because queries and performance degradation in the case of a defense, they can be objectively measured. You can quantify a query. You can quantify how much your performance goes down if you apply a defense, but it's difficult to translate in an objective manner how much of an effort it takes for someone to develop a given attack. But this is something that perhaps should be encouraged. Some hints that we put in the paper, which coincidentally I came to know about them after I came here to the University of Liechtenstein, is like try to identify the, like try to measure the time it takes to write code. Perhaps you can look at the commits history on GitHub, or you could try to truly quantify how much hours it takes for someone to come up with the attack that actually will result in the final product, in the final attack itself. Because I mean, we do not have to forget that there is someone that has to come up with the tactics, and sometimes these entails some failed experiments. And I think real attackers, they do encounter a lot of failures. And perhaps it could also be put in the paper itself, like perhaps focusing more on some negative results. These are all things that should be mentioned, that like real attackers do factor in, or I think they do factor in before even attempting to do something. So just saying, hey, we came up with an attack and it takes $3 to crack GPT-3. Well, because of like few queries, that may be a bit too simplistic in a way. So we should try to explore more things. We do not have a concrete solution, but it is something that we would like future efforts to work on.
David, go ahead.
Yeah, I mean, that's exactly my thoughts exactly. And basically, there are so many different types of costs, right? There's machines, there's human time, there's number of queries, you know, there's, I don't know, whatever else you need to, you know, I mean, some of these things are actual businesses, right? You need, you know, facilities and you know, janitorial staff and all these things. And like you were saying, okay, like you know, in a perfect world, we'd be able to convert all of this to dollars and compute the dollar cost of any particular attack. and this is going to be basically impossible to do because of all these different factors involved. So I mean, yes, computing cost is something we struggle with. We know that that's what actually matters, but it's very hard to measure and compute and compare. Right? What we really want to do is say, okay, we could do A or B. Which one would increase the cost more? Like one of them might require more queries, one of them might require more computation per query. How do we even compare that?
You know, a listener brings up a great point, is that there's also cost sensitivity. And that is like, even though it might be really expensive, like a nation state conducting an attack might be insensitive to that cost, even though it's expensive, right? Like the different attackers are going to have different sensitivities to how much something might cost. I think that's a really great point. And part of some solution that all you smart listeners should come up with about how to frame economics around attacks and defenses. Another thought I had is, like ChatGPT or whatever, like machine learning machine learning systems are becoming the major part of the system now and the most public part. And they're becoming, I think, attackers to ChatGPT, to jailbreak it, to do prompt injection, are still guessing. All these things are true, but now maybe there's a slight change in the narrative about economics and how things are happening. I'm interested in your thoughts. What is? I mean, we wrote this paper kind of before the ChatGPT craze. How are these positions holding up as of February 2023, especially the economic considerations? Any thoughts?
I could have thoughts. First of all, these are my thoughts today, but it's something just for me to also elaborate. I guess it would be a process for all of us, in a sense, to elaborate how these technologies may change. But on the one hand, I think we're not necessarily facing something that is too different from what we have observed also with botnets, for example, right? Even with the botnet threats, they started creating toolkits and programmable things, or just for $15 or $50, you could take down a major competitor or a major service or website for a week. So yes, it would definitely have an impact on security and the economics of attackers. I think that maybe it's one of those things in which people start to realize it more, but I think that there has already been a scale down in costs for attackers. If you just think about the computational power, even of laptops or mobile phones, that they increase over years, even about even just brute forcing attacks, right? So at the moment, that is my view, although I don't think we have the major picture. What concerns me a bit about ChatGPT and this technology, on the other hand, is also I'm partially concerned about privacy, which I know that in a sense it's a separate aspect that the attackers may not even care about. But
there's also comment from the audience maybe about ChatGPT that's relevant. That's since attackers guess, can these tools be used to automate the guessing? Does that also change the economics of an attack from at least a time perspective?
I think so. I think that as with any technology, if it's good, attackers will use it. So it's a double-edged sword, right? And I think that even though it will mostly for good, I think that there may be attackers who want to use ChatGPT for making things easier. I mean, I think that anybody who is into software development has seen how disruptive ChatGPT can be when it comes to facilitating like software development and writing code, I was impressed, like, and how much the productivity of a single person can improve by using it. So I think that real attackers would definitely resort to that, and that would like lower the barrier of entry for attackers. Of course, hopefully defender will use it as well, and perhaps the thing will be kind of balanced, but definitely attackers, I think they will use it. I don't think there is.
I mean, as an additional note to that, I think that there is imbalance also here, I feel, because generating attack code may be easier than generating secure code, which is the same issue that we had when GitHub Copilot came out. There was also a best paper at SMP 2022 that was evaluating how much insecure code GitHub Copilot was automatically generating, because I didn't have an intrinsic concept of security. It was not magic, so it had a lot of training data from GitHub, from just maybe even student projects that didn't know about SQL injection. And so unfortunately, I feel that at the moment it may be more, it could be more useful for attackers than for defenders, but
I want to, we're quickly running out of time, and there's so many positions in the paper, we're not going to get to them all. But I thought I'd bring up, based on some questions in the chat, the position on, the recommendation about defining the knowledge and the capabilities of an attacker, and how those today can be inconsistent or muddled. And even during our chat, the authors of this paper who recommend not using white box, black box, we're doing it because it's so built in, it's so hardwired. What's the new recommendation? Like, how would we change this? If you could wave a magic wand and say something different than white box, black box, what would it be? Can we talk about that for a minute?
Yeah. In the paper, we say to use perfect knowledge, limited knowledge, or no knowledge. And this should be, by extending it to the system perspective, you should say what the attacker knows and what the attacker can do for every component that makes up the system. So the attacker has knowledge of this component, or has partial knowledge of this component, and then has knowledge of this other component, or partial knowledge, or no knowledge whatsoever. It depends. But the point is, let's try to expand it to the whole system perspective and try to use more precise ways to define it. And we think that using full knowledge or perfect knowledge and intermediate or limited knowledge, it's less ambiguous than just white box or black box or gray box. But of course, it will take some time before these, hopefully it will, but it will take some time before these goes away. But this is probably the way forward. Because truly, if you look at the examples we provide in the paper about the usage of white box terminology, there are things that go in complete opposite ways, despite being defined as in the same way as black box or white box.
I think another element of this is when we talk about attacker capabilities and knowledge, academically, we always tend to jump to the worst case. Adversarial machine learning, by definition, is considering worst case conditions for machine learning, right? Where practically, that's kind of a severe position to take. We might often want to take a common or prevalent security position rather than a worst case. This came up just today. We were talking about what would a nation state do? Look, that's probably not your biggest threat today, right? Your biggest threat is the kiddie script people against your machine learning model, and that's a far more important for most industries, probably a far more important a threat vector. And to define what those capabilities, what that knowledge looks like, how you'll defend against that, right? Are there other ways that we can refine practically how we frame a defensive position with respect to, the box terminology, knowledge, and capabilities of an attacker?
That's a very hard question to close by, right? To close with. I guess it could also, I mean, as we were discussing before, it's maybe it's not even about boiling it down to just a single term that's, well, or maybe in a sense we need to expand the terminology so that we have more scenarios that can be captured with maybe a single word. But I think a lot depends on the ML system that is available and the knowledge on all these components. And the more, of course, formal we can be and capturing nuances, then we can start having even a framework where, I mean, I think that the Holy Grail, at least for me, will be having a sort of framework where maybe then it becomes a checkbox exercise in a good sense, in which throughout the system you have a list of things that could be considered or not. So we have to work more on the granularity of the knowledge that we are talking about. I mean, the box terminology are part of being non-inclusive, and we should be making an example, actually. It's also too simplistic, and that's where the consistency was coming from, in my opinion.
Yeah, something I would like to add about this is, because if you want to part away, the economics is probably one of the starting point that we should also look into, because you take up a research paper and you read, we assume an attacker with white box knowledge, an attacker that knows everything about the target system. How? I don't think that even the developers of the machine learning system know everything about the system. So how do you assume an attacker that knows everything about the system or the model or every component? I mean, that takes a lot of time. So if you assume an attacker that has perfect knowledge, you should say, okay, how much of an effort did that require? And if you look at it in this way, perhaps you could try to see, well, perhaps an attacker, instead of doing this, they would be able to do something completely different. Of course, we are doing research here, or like researchers, they have different goals. They do not try to completely portray reality. But if some papers start to take this into account, then perhaps we could discover some interesting ways that real attackers can use to achieve their goals and to successfully bypass real machine learning systems. And this could be one way to bridge the gap between research and practice.
You know, one of the solutions to all of this conversation might be, as David has brought up, better collaboration between industry and academia. David, do you want to just close us out with any comments about that?
Yeah, I think, I mean, the fact that we're here discussing this points to a successful collaboration between industry and academia. And it's you know, it's about creating the opportunities. So yeah, we had this doctoral conference, which was a fabulous opportunity for a small group of people. I think I'd encourage people at companies, you know, reach out to people working in the field or people at local universities. You know, for academics, you know, the warning to academics, like sharing data is difficult. Lots of hoops to jump through, like lots of risk involved. The path of least resistance is to bring researchers in, you know, as contractors and, you know, interns and, you know, short-term, whatever, so they get internal access. I've had success with this both at Meta and at LinkedIn, where I worked previously. And, you know, we see academics, you know, they can understand the technical problems, they understand the security part, they can quickly pick up context on the business problems. And, you know, it's a mingling of ideas, and it really bridges the gap, and kind of gives more insight on both sides. So just, you know, keep communicating, you know, more forums like this, like Dagstuhl, and you know, local engagements.
And for all of you who have joined us today, I think we're taking a step in that direction. Thank you. And Giovanni, Fabio, David, thank you. This has been wonderful. I think very practical and crunchy in the observations made in the paper. And with that, we'll wrap up our webinar. Please feel free to reach out to me, to our co-authors, if you have a desire to continue this conversation. With that, we will sign off. Thank you very much.